Okay. Well, as I'll get started because we only have one period together today, and really, as soon as you arrive, just quickly type your name down, and I'll make sure to add it as we go along. All right. Now, what I wanted to do for this one period, I looked at what we did last time on compound interest, and I realized that as I was saying the formula, I corrected myself, but it was very muddled up, for lack of a better word. So what I'm going to quickly do here is I'm going to redo the same type of question that we had last time, and that was on exercise 2, okay? Last time it wasn't Kathy, it was Benjamin, I believe, if I remember correctly in the question. But so the purpose of this really is to give you the formula again, to properly define each parameter, and that's the formula for compound interest that we have here, okay? But also I want to highlight how it's closely linked to geometric sequences. And so I think that'll come out quite nicely today, okay? So let's see. We're told in this first exercise that Kathy invests 8,000 euros with an annual rate of 12%, which is compounded quarterly. Remember, we saw last time that when we're told compounded quarterly, it basically means 4 times in a year. Put simply, every term or every trimester that goes by, interest is compounded, okay? We need to do 2 things. The first, we need to calculate how much Kathy would be worth in 4 years, or I could have written after 4 years. We then asked, how long will it take for her to double her investment? Okay, now, when I say that, I'm assuming, of course, that she's not taking of the money out, so the money is just, deposited and left to rest with that annual rate for whatever time is needed. Okay, that's the whole idea here. So let's see. First, I'll remind you of the formula that we saw last time, okay? And this time we'll define everything quite nicely. The idea, for me to calculate how much an investment will be worth, and I'll call that the amount, for me to calculate the amount I have, which I'll call A, when I invest an initial amount, which I'll go ahead and call P, at an annual rate R, which is compounded n times per year, we can write this. The amount A we have is equal to P times, in parentheses, 1 plus R over N, all of which is being raised to the power of N times T. Now I'll go ahead and box that, and just as I did last time, I'll define everything we see inside this formula, okay? And this is where in the last class, I know I got muddled up between N and T, if I remember correctly, so I really want to make sure we do this properly. Do make a note of this. When I look at that, going from left to right, A is the amount we have after T years. After T years. Okay? So just to be clear here, the T is what we see right here, and that will always equal to the number of years that have gone by. Okay? Next, we have P, and that's the initial amount we invest. Okay, that's the initial. So in other words, in this case, Kathy goes to the bank, drops off 8,000 euros. So P in this case would be 8,000 before any interest has been applied. Next in this, we have R here, and R is the annual rate, and I should specify expressed in decimal form. So in decimal form, and what I mean by that is, for instance, if we had 30% in decimal form, that would be 0.3. Okay, that's what I mean when I say expressed in decimal form. Finally, we have N, and that is the number of years that go by, I suppose, that have passed. I'll just say gone by. Okay, there. Okay, now that is exactly what you should have, or you should write that down. Okay, that's the formula we're going to be using as soon as we calculate anything with compound interest. With that formula, provided we know it, answering this type of question or these questions is actually quite straightforward, and I'll show you what I mean by that. All I have to do really is just directly apply it. So I'll use a couple of different colors here. For question A, I'll use this color. And I'll go ahead and do that here. Or actually, I'll do it at the bottom here. Question A. Now, we want to know how much Kathy's investment will be worth in 4 years' time, or after 4 years have gone by. So in this case, the 4 years, your immediate reflex has to be, okay, well, the variable that takes the time here is t, right? So in this particular question, we know that t has to be equal to 4. Furthermore, reading through the question, we know that the amount Kathy initially invested was 8,000 euros. So that would be the initial amount. That's going to be P. So capital P equals to 8,000. And on top of that, we know that the rate is 12%. That's the annual rate. And so I can go ahead and say, okay, well, R is equal to 0.12. That's 12% expressed in decimal form. And finally, since we're told that the interest is compounded quarterly, that means it's going to be compounded 4 times a year, right? So let's see. N will be equal to 4. And as I'm writing that, I can see that already up here, I didn't define t. And I've done that a bit like last time, actually. So what I'll do is t is the number of years that have gone by, and n is the number of times interest is compounded. Something about this formula that always makes me write n as the number of years. But anyway, so n is the number of times interest is compounded each year. Okay? All right, now, going back to our question here, t equals to 4. P is the initial amount, 8,000. R is the annual rate expressed in decimal form. And n is the number of times the interest will be compounded in a year. All we have to do now is plug all those values inside this formula. In doing so, let's see what we get. The amount that Kathy will have, or the amount her investment will be worth after 4 years, will be 8,000 times, in parentheses, 1 plus 0.12, that's the rate, divided by 4, the number of times it's compounded, all of which is being raised to the power of 4 times 4. So in this case, 4 is the number of times it's compounded in a year. The second is the number of years that have gone by. Okay? So at this stage, we could simplify this a bit. I mean, mind you, it would be a calculator paper. So you could just calculate all that in one go with your calculator. But if I simplify this a tiny bit, we should be getting 8,000 times 1 plus 0.12 divided by 4, which will be 0.03, all of which is raised to the power of 4 times 4, which is 16. And that quickly leads to A equals to 8,000 times 1.03 raised to the power of 16. Okay? At this stage, we get our calculators. So I'll just make my calculator appear here. There it is. And yeah, that should fit right there, I believe. Yeah, that's not too bad. Okay, so let's see. With this calculator, I'll go ahead and calculate that. We have 8,000 times, we don't really need those parentheses, but I'm going to type them anyway, 1.03, and that's raised to the power of 16. Oops, not 6, 16. There we go. That's all typed correctly, I believe. Type enter, and that's how much her investment will be worth after 4 years. So if I try and write that down properly, that's 12,837.7. Okay, and technically we should always write any money, or I should say currency, with 2 decimal places. Okay, to go down to the nearest cent. Okay, that's the answer. Right. Next question. How long will it take for her to double her investment? Well, if I'll use a different color here. Let's see. For Kathy to double her initial investment, that means, we're trying to figure out, question B, and I'll hide my calculator again because I can see I'm hiding my own writing. We're trying to figure out in question B, how long until until A is greater than, well, 2 times 8,000, so that would be greater than 16,000. That's what we're trying to figure out here, right? But now, we have an expression for A. It's the entire right-hand side of this formula here. So basically what we're trying to solve here is, okay, when will P times 1 plus R over N raised to the power of NT be greater than 16,000? Yeah. And we can definitely complete this further, right? I mean, we know what P is, we know what R is, we know what N is. So, filling all that information in, this turns into, okay, well, 8,000 times 1 plus, 0.12 over 4 raised to the power of 4t has to be greater than 16,000. And simplifying this leads to 1 plus 0.03 raised to the power of 4t greater than 16,000. And finally, we have 8,000 times 1.03 raised to the power of 4t has to be greater than 16,000, right? That's what we're trying to solve here. But now, at this stage, I find it quite useful to divide both sides by 8,000, okay? Because if you were to plug this directly in your calculator, in other words, if you were to plug the curve y equals to 8,000 times 1.03 raised to the power of 4x, and you were to plot the line y equals to 16,000, the scale, just the sheer scale of those numbers is such that it's going to be a real pain. You're going to have to scale the window properly. It's going to be way up there on the y-axis, and it's just not going to work out nicely. So instead, what we can do here, if I divide both sides by 8,000, that's going to lead to a much simpler inequality to solve. We'll end up with 1.03 raised to the power of 4t greater than 2. Okay? That, with our calculator, we can quite easily solve. And at this stage, I'm going to show you two options. Okay? Two ways of solving this inequality. The first is to do it graphically. And in fact, quite frequently, students tend to prefer doing it this way, and I completely understand why. I mean, you got a calculator, and if you want a graphical method, here's how we would do it. I'll show that to you right at the bottom here, and I'll just go, okay, I'm going to plot, and I'll say option 1, and I'll just say in parentheses GDC, graphical display calculator, okay? So what you're going to plot is y equals to 1.03 raised to the power of 4x, and you're going to plot y equals to 2. And so what you're going to try and figure out is when does this curve go higher than this line? Here's what I mean. If I take my calculator out, I'm going to have to put that on the far right-hand side of the screen, I believe. So I'll quickly show my calculator again. There it is. Okay. Now, if I go ahead and select the graphing option, the first curve I'm going to plot is y equals to 1.03 raised to the power of 4x. Okay, that's the left, that's one of the equations, so I plot that. We can see sort of increasing, it's an exponential curve, increases slowly, and don't worry, I'm going to zoom out in just a second. I'll just delete that label though. There. And I also want to plot the line, let's see, I want to plot the line y equals to 2. Okay, and so if I do that, so I'll just quickly add another graph. So I go menu, I should be able to graph entry, and I go to function, and I'll just draw the line y equals to 2. Done. Okay, and again, I'll get rid of that label. I find that really inconvenient. Now, for the sake of seeing that properly, I'm going to zoom in a bit. Okay, so I'll just change the window settings. You wouldn't have to, but just for the sake of seeing things properly, and let's say I go from -1 to 15, and the y-axis I'll go -1 to 5. Okay, so we get a much better view on it. Now, to be clear, what's going on here is this blue curve is the exponential function we have. The red line is this horizontal line, y equals to 2. So when we look at the inequality that we have here, and in fact I'll box it in green just to really get your attention towards it. There we go. When I want to solve that inequality on the graph, this is basically telling me When is the curve 1.03 raised to the power of 4t higher than, greater than, think higher than 2? And we can see that as soon as, once the two intersect to the right of that point, the curve is definitely above the line. So if we look for that point of intersection, I go to Menu, and I go to Analyze Graph, fourth option, Intersection. For the lower bound, I just go anywhere to the left of the point, I click, and for the upper bound, anywhere to the right, and I click. And we found the point, right? The x-coordinate is 5.86. We're not interested in the y-coordinate, only the x-coordinate. Now, here, we find that they intersect when x equals to 5.86, and therefore, for this curve to be above the line, we need x to be greater than that x-coordinate. So x has to be greater than 5.86. Now in an exam though, remember what you're actually dealing with here. The variable isn't x, it was t. So as silly as it may sound, do make sure to actually state your answer in terms of the variable. So t has to be greater than 5.86. That's the solution. Okay, so 5.86 years is how long it would actually take. We could be asked to break that down into months, or even, since it's compounded quarterly, we could be asked to break that down into terms or trimesters. Not going to do that right now though. Okay. Second option. That's one way of solving this. Second option, and for that I'll just quickly hide my calculator for a second again. Second option, let me hide this first, there we go. The second option, which I'll write at the bottom here, option 2. Option 2. In parentheses, I'll just say logs. Okay. Now, to be honest with you, if you're in an exam room or you're at our end of year exam, go for the first option, right? If you're given the choice between using a graphical method or going deeper into algebra and figuring out by logarithms, minimize the risk of making a mistake by just using the graphical method. On the other hand, if the calculator actually clearly states or makes you, better word, use logarithms, this is how you would do it. You'd get as far as here, right? That's the result we had. So starting from that, if I just copy that, we have 1.03 raised to the power of 4t, and that's got to be greater than 2. What I do is I apply logarithms to both sides of that inequality. And remember, the base doesn't matter here, so I'm just going to go ahead and say log base 10. And for that, I just write log of 1.03 raised to the power of 4t has to be greater than log of 2. Now that that's done, I apply the third law of logarithms to take this exponent out. Remember, I'll write that at the top of the page here. If ever we have log of any base b of some number a raised to a power of x, then that's equal to x times log base b of a. Okay, we had seen that already. Applying this law to this inequality, in particular to the left-hand side here, leads to 4t times log of 1.03, which has to be greater than log of 2. Finally, if I divide both sides by 4 times log of 1.03, so I leave the t alone, I just take the 4 and the logarithm, this turns into t has to be greater than log of 2 over 4 log of 1.03. Okay, I can see that's getting a little bit small there, isn't it? So I'll just shrink the picture of me for a second. There we go. Okay, and now with my calculator I can actually calculate that. Okay, so I go ahead and calculate log of 2 divided by 4 times log of 1.03. So if I just quickly take my calculator again, and I'll just make it appear, and I'll move it to the far left hand side, like so. Okay, so if I go back to the scratch pad, let's see, I have to get back to my actual calculator on my screen here, there it is. I want to calculate log of 2 divided by, in parentheses, 4 times log of 1.03. And I exit all that. Enter. And again, no surprise, I get the same result as we did previously, which is 5.86. That's the answer, okay? So t has to be greater than 5.86, right? So that's how long it would take her to actually double her investment, okay? Which, all things considered, doesn't seem that long. So it is worth pointing out that 12% annual rate is huge, okay? That is a massive annual rate. And the only way you could potentially get such an annual rate would be with high risk, okay? But I chose 12 for the sake of this question. Now, with that in mind, what I'm going to do, and I'll quickly hide this calculator again. What I'm going to do, we had finished the last class in which, I left you with an exercise to do in which something had to be compounded monthly. So 12 times a year, not 4 times a year. I've actually sort of repeated that with this exercise here, and so I've got the same type of question here, but on the next page I'm going to compound it monthly. Okay, so same investment. Kathy invests 8,000 euros with an annual rate of 12%, compounded monthly, and we're asked what will her investment be worth in 4 years, and then how long will it take for her to double her investment. Right, well, if I quickly copy that formula again at the top, remember the formula for calculating the amount we'll have after t years when investing an initial amount p at an annual rate of r compounded n times per year. We use this formula in which that pair of parentheses is raised to the power of nt, where t is the number of years. Okay, so without thinking too much, I can just go ahead and use this formula again, right? And in doing so, let's see if I'll do it in white here. Question A. The amount she'll have after 4 years. Well, let's see. I would go ahead and say A equals to, so P, the initial amount, let's see, it's going to be 8,000 again, times in parentheses 1 plus the annual rate, which has not changed, right? It's still the same. So the annual rate is still 0.12, which is 12% expressed in decimal form. And I divide all of that by the number of times interest is compounded. Now, given it's compounded monthly, in this case, n will be equal to 12, okay? And all that's being raised to the power of n times t. So n, again, is 12, and that's 12t, okay? Now, this is a sort of generalized formula, and in fact, I could simplify that a bit and make a special note of it to save time for the second question. That's 8,000 times 1 plus 0.12 divided by 12, which is going to be equal to 0.01 raised to the power of 12t. And finally, A is equal to 8,000 times 1.01 raised to the power of 12t. Now notice here that I've deliberately not replaced t by 4 yet. And the reason for that is I would recommend, in a question like this one, to get this formula. In other words, all it is really is the simplified version of the initial formula. Okay. Now that I have this, I'm really, I'm good to go for the rest of the question. Let's say I want to plug this in a calculator. This is the simplified version. I would just have to plug y equals to 8,000 times 1.01 raised to the power of 12x inside my calculator. Right, so I'm just saving time here. Now, that's an intermediate result, though. For me to actually calculate how much you'll have after 4 years, all I have to do is replace t by 4. Let's do that. That's going to be A equals to 8,000 times 1.01 raised to the power of 12 times 4. That's equal to 8,000 times 1.01 raised to the power of 48. Finally, with a calculator, and so I'll just grab my calculator here, make it appear again, and I'll move it to the far right-hand side. With a calculator, we get 8,000, so let's see, that's 8, let's get that wrong, there it is, 8,000 times, what do we have, 1.01 raised to the power of 48. Yeah. And we get that. That's 12,897. Let me just write that. 12,897. and 97.80 euros. And I'll go ahead and underline that result. Now if I quickly flick back, what did we have before? And I'll write what she had before in green here. 12,837, so that's compared to 12,837.70. That's what she had in her when it was compounded quarterly. Again, may not seem like a massive difference, but I mean, you know, if we were talking in millions or billions of euros or dollars, then, you know, that difference is actually quite a bit, right? It's all relative to the amount you start off with. So there is a difference between compounded monthly, quarterly, or just annually, right? It makes a big difference. Now, we've answered that question. If I move on to question B, how long will it take for her investment to double? You know, you're probably guessing, yeah, it's going to take less long, right? Because it's being compounded monthly now, which basically means that this thing is growing faster. And when I say this thing, her investment, right? So let's see. If I go ahead and first I'll move the calculator a tad, like that, okay? And if I go ahead and actually calculate all this, what will we have? We're trying to figure out when this amount A, when will this be greater than, let's see, double her investment, so greater than 16,000, 2 times her initial investment, right? So what we're trying to figure out here is when will we have 8,000 times 1.01 raised to the power of 12t, when will that be greater than 16,000, right? Just as I did in the previous exercise, I can go ahead and divide both sides by this 8,000, and it's just going to scale things down rather massively. Yep. So if I do that, that turns into 1.01 raised to the power of 12t, and that's got to be greater than 2. Okay. Now, again, at this stage we have an option: either use logarithms or use graphical methods. I'll go ahead and use the graphical method again. Okay, so if I do that with my calculator here, and if I go back to the graph, well, actually what I'll do is I'll clear my scratch pad first. Clear scratch pad there, so we start fresh. And so, on one side, and if I use a different color again, on one side of this inequality, I've got this function, so I'll go ahead and plot y equals to 1.01 raised to the power of 12t. And on the other side, I've got that function. It's a very simple function. It's still a function, though. And its equation is y equals to 2. So if I plot both of those, that's 1.01 raised to the power of 12x. Careful, we're not going to put t. That's the first graph, so I plot that. And I add a second thing to my graph entry function, just f of x equals to 2. Done. Okay, again, I'm going to get rid of these labels. So if I just delete that, I'll delete this as well. And I'll scale things nicely so that you can see. Window, I believe I went from -1 up to 15, I think. Then y min, I'll go -1, and y max, I'll go 5. Okay, there. Now we have of both the graph and the horizontal line. And we can see quite clearly, you know, the curve goes higher up or is above the line once it passes this point. So really, the whole problem reduces down to figuring out the x-coordinate of that point. So if I go click on menu, analyze graph, intersection of this curve, so I click here, and I click here, and there we have it, 5.81. Okay, so here we can see that t has to be greater than 5.81. Again, in an exam, you would actually say, you know, with, in parentheses, with calculator or with GDC. Okay, just to tell the examiner that's how I did it. You could even go as far in an exam, in an official exam, and in fact I would recommend you do, you know, with calculator and actually make a sketch of what you're seeing. So it looks really nothing major, right? Just something very straightforward looking like this. And you would actually label the coordinates of the point, 5.81 and 2. And this is the line y equals to 2. That's the curve y equals to 1.01 raised to the power, that's 1.01 raised to the power of 12x. Right, that's quite literally what you would sketch in an exam. And you know, they have to give you the marks on a calculator paper. Okay? And that's the whole idea here. Okay, so really that exercise shows us, you know, once again that, yeah, it takes a little less time. If you think of it, I believe the previous exercise we had 5.86 of a year, if I remember correctly. Let me check. Yep, we had 5.86, and so now we have 5.81. So it does take less time, and if you're given the choice between the two, even if it's not a massive difference, if you're given the choice between the two, you're likely to opt for the one that grows fast, and so therefore she would probably choose whichever bank this is, right? Which would make sense. Okay, everyone, so that really is the idea behind these formula, okay? But I will show you one last thing. And like I said at the beginning, I wanted you to see and really understand the connection that was to be made with geometric sequences. Because although I mentioned it, I don't think I haven't brought it to light yet, okay? So what I'll do, I'll spend a few minutes on that. And I'm just going to hide my calculator one last time. And I'll use that space I have in the upper right-hand corner. What if, and I'll go back to the initial question here, question A, okay? Let's say for a second you didn't have this formula, okay? You just didn't have it. And just to make it clear, I'll box that formula and sort of, keep it there aside. That's my compound interest formula. Let's say for a minute that we did not have that formula, and I gave you this information, right? Compounded monthly and so on. And I told you, okay, what will Kathy's investment be worth in 4 years' time? Now, because it's compounded monthly, this question would be a real pain to answer if we didn't have a formula like this one. If it were compounded annually, yeah, maybe. I mean, you could definitely calculate the first 4 terms of a sequence. Here's what I mean. Every single time interest is compounded, every single time, and I'll just write it at the top here, I'll use green, every time, so every month, interest is added, okay, every time we add 12% divided by 12%, divided by 12, right, number of times in a year. Now that's equal to 0.12 over 12, and as we saw previously, that's equal to 0.01. Okay, so basically, with this scenario, in this particular bank, every month, the amount Kathy has is being increased by 1%. That's basically what that's saying. Therefore, every month, and I'll call, P, the initial investment, P is multiplied by the percentage increase multiplier, and it's being multiplied by 1.01. Here's what I mean. We start off with P. A month goes by, we have P times 1.01. A second month goes by, we have P times 1.01 times 1.01. The third month goes by, we have P times 1.01 times 1.01 times 1.01. And I'm sure you can see where I'm heading with this. This would be 1.01 squared. This would be 1.01 cubed, and so on and so forth. But here comes the problem. There are 12 months in a year. So for you to figure out how much, Kathy's initial investment is worth after 12 months' time, you'd basically be calculating this. It's P times 1.01 raised to the power of 12. Okay? And that's going to happen each and every single year. And that kind of explains, if you can see this P times 1.01 raised to the power of 12 and compare it to what we have here, as such, this 8,000 is P, right? That's the initial amount she had to invest. And that's where this, this 12 here is the same 12 as we have here. Because every year it's compounded 12 times, which is why you have this power of 12. Okay? And we're going to repeat that entire process T times, in the sense that, T years, or 4 years in this particular question. But I'm sure you can appreciate that this is rather tedious. Okay? You don't want to calculate this, because you'd have to carry on here, right? And you'd quickly carry on and say, okay, well, after maybe 2 years, it would be 1.01 raised to the power of 24. After 3 years, it would be 1.01 raised to the power of 36. After 4 years, you'd have p times 1.01 raised to the power of 48. And that's exactly what we got to here, okay, raised to the power of 48. Hopefully that makes sense. So in other words, hopefully you can see here that what you're dealing with is, this is a geometric sequence, right? I mean, that's exactly what this is. I'm always multiplying by the same amount, okay? After the first month, I multiply by 1.01. Then to get how much we have the second month, we multiply by 1.01 again, and so on and so forth. That is a geometric sequence. We're always adding by the same amount to get the next value, okay? Now, what this highlights is the fact that, geometric sequences and exponential growth go hand in hand. Okay, they're the same thing. Okay, the graphs that we saw a minute ago, and the sort of rather, albeit lousy sketch I made here, that is exponential growth. So when you invest money in the bank or you leave money to sleep in a savings account, you're counting on exponential growth. If maybe some of you already do. It would be a fun question to ask your banker, how frequently is interest compounded? And you may find he or she doesn't know. And if they do, you'll probably find it's going to be quarterly. I believe most banks do that now. Okay, but nonetheless, it's an interesting question because you're investing money, and if you invest money somewhere, you'd like the person you're investing your money with to be able to answer the question properly. So it could just be a quick trial to see if your banker knows his or her math properly there. Okay. And it could be an interesting experiment. Point is, the IGCSE examination board, I believe, quite likes this type of question because of how much room it leaves for making a question on geometric sequences, exponential growth, logarithms. It can combine all those things as well as use of technology. So good use of your calculator. So you want to make sure you work through these two exercises a few times. I'm going to be sending you some as well. Okay. But this is really one of those at IGCSE would be paper 4. One of those paper 4 questions that you really, really, have a good feel for. Okay, everyone? I saw in one of the comments that, no, it wasn't exactly the same question as last time. Okay, don't worry. I'll gladly share the exact correction of the one last time. I didn't have it, at hand, and just before I just changed the numbers and the names, essentially. But the essence is there, okay? And again, I've got a question about, I'm just reading as we finish. Yes, and sorry, one of the questions, I'm glad I just read that question. One of the questions that's been asked here is whether or not you're going to have this topic in the exam. And my answer is, yeah, very likely. Very, very likely because of how many things I can do with it. Okay, I can have, essentially, I can write a question in such a way that, yeah, I'm going to combine your skills in functions, or as we've just seen, geometric sequences. Or, as we saw in the previous question, logarithms, right? So, yeah, this is a type of question which is definitely an extended IGCSE question and quite likely could be at the exam, okay? Now, on that note, I'll let you all go because it is time and you need to get to your next class, okay? The topic's exact bullet point list coming on Matchback, okay? Very soon, promise you that. For now, though, everyone, I'll leave you there and take care of yourself. I'll see you next class.